Well, greetings of the day from Total Output Power Solutions. This is the thermal power plant cycle that you are seeing in, and this is a coal based thermal power plant, and today we will be discussing about the 210 megawatt turbine cycle heat balance. So we will be discussing about the all the equipments those are there, and then we will discuss about the heat rate. So this is the cycle that is for 210 megawatt steam condensate and feed water circuit. The red lines they depict the steam lines, the green one those depict the condensate flow, and the blue ones they depict the feed water flow. So normally, and some drains are also shown in the figure. Some drains are there, some extractions are there. So those have been marked accordingly. You can go through that. So first of all, we see what are the assumptions those are being made for the heat balance that is being calculated in the next slides. The undercooling in the drain coolers of heater number 6 and heater number 7 is 10 degrees centigrade. The effect of drain cooler of heater number 5 has been ignored. When pressure in heater number 5 approaches 10.5 kg per square centimeter absolute, drain from heater number 6 is diverted to deaerator bypassing heater number 5, and drain of heater number 5 is diverted to heater number 4. These are the assumptions being made. The first you see the equipment that comes in the regenerative heating system is we start from the steam ejector. So the steam ejector gets the condensate from the CEP, condensate extraction discharge pumps, and this condensate passes through the steam ejector, or you can say the steam ejector cooler, and the steam ejector gets the steam from deaerator, and which is used for making vacuum in the condenser. Now this steam is then condensed and it goes to the flash chamber drain itself on the condenser. The respective parameters are shown here. The temperature, inlet temperature of the condensate to the steam ejector, that is 43.16. The inlet steam that is taken from the deaerator has got a pressure of 4.5, temperature of 155 degrees centigrade. The flow is mentioned and the enthalpy is also mentioned. Now this steam is converted into drain or the water, and the temperature comes to 47.27 degrees centigrade. Then the pressure is 0.09 kg per square centimeter absolute, and the flow is been mentioned there, the enthalpy is also there. Now with this you can calculate the condensate temperature, outlet condensate temperature, considering that the steam ejector efficiency is around 99.8 degrees centigrade. Absolutely you can measure the temperature also, but it is calculated here, and that temperature comes out to be around 45.07 degrees centigrade. The calculations are also shown on the screen. The next in the regenerative system comes the gland steam condenser GC1. Now we are using steam for the glands, and that steam when supplied to glands comes out from the glands, and that is a air steam mixture which is from the outer glands of the steam turbine. So this air steam mixture, this comes out from the glands. Again the steam is also supplied from deaerator for the ejector for making some vacuum, so that the steam air mixture comes from the outer glands. So both these inputs, the pressure and temperature, are shown there. Now they don't mix with the condensate, but the condensate from ejector passes through the gland steam cooler GC1, and the outlet of the condensate, it goes to the LP heater 1. The drain from the gland steam condenser number 1, it goes to the flash tank itself on the condenser itself, means it is in the condenser itself. The respective flows and the enthalpies and the temperatures are mentioned on the diagram. You can calculate the gland steam condenser efficiency, which comes out to be around 99.7%. Then next in the regenerative cycle comes the low pressure heater number 1. The condensate from GC1 enters the low pressure heater number 1, and then it goes to GC2, gland steam condenser 2, the condensate, and in the process it gains the temperature from 47.18 degrees centigrade to 61.05 degrees centigrade. This steam is supplied to this LP heater number 1 from the extraction E1 and from LPT. It is in the condenser itself. You will not be able to see it outside the condenser. It is in the condenser. So in the condenser the extraction is there, and this extraction is given to this LP heater number 1, and the extraction pressures and temperatures are shown here. Again the drain of this, it again goes to the flash chamber in the condenser. You can calculate the efficiency of LP heater number 1. It comes to 99.8%. The next in the regenerative system is the gland steam condenser number 2. Now in this case the condensate from LP heater number 1 is passed through the gland steam condenser number 2, but 80% of the condensate passes through and 20% of the condensate is bypassed, and the temperature gain is from 61.05 degrees centigrade to 68.10 degrees centigrade. The drain, again it goes to the flash chamber in the condenser itself, and the extraction steam that is supplied is from the HP and IP glands, or the from the glands of the steam turbine, inner glands of the steam turbine. The efficiency of this gland steam condenser GC2 comes out to be around 80%, because 20% of the condenser is bypassed. Otherwise it would come to around 99.8 or something. So this way the efficiency can be found out. Then in the next condensate path is the low pressure heater number 2. The condensate from gland steam condenser number 2 with a temperature of 68.10 degrees centigrade passes through the LP heater number 2. So in the LP heater number 2, when the condensate passes through it, it gains a temperature of around 100.86 degrees centigrade. Now here the drains from the LP heater 3, they are added into LP heater 2. Again the extraction steam from IPT out, that is the E2, extraction E2 is there. This steam is going to heat the condensate, and the drain from LP heater 3 is added in the LP heater 2. Now resulting is that the temperature of this drain from the LP heater number 2 comes out to be around 105.78 degrees centigrade. Now this there is some flow. This flow is again supplied into the condensate line. So you will see that the flow going to the GC2, going to the low pressure heater number 2, it gets increased. The output of the LP heater, the inlet going to the LP condensate inlet going to the LP heater number 3, that increases by the amount of the drain that is coming out because of the drip pump. So this has been very well shown in the diagram. You can see it in the diagram also. The efficiency of the LP heater 2 can be similarly calculated. It comes out to be around 99.8%. The next in the regenerative cycle is the low pressure heater number 3. So in the low pressure heater number 3, the condensate from LP heater 2, it passes through the LP heater 3, and the drain of the LP heater 3 goes to LP heater number 2, as we have seen in the last slide. The total condensate to LP heater 4 is the same, that is from the getting from the LP heater number 2, that is the same, but the temperature increases from 101.52 degrees centigrade to 125.27 degrees centigrade. The drain from LP heater 4 is also added in the LP heater 3, and the extraction steam is taken from the IPT extraction E3. The pressures and temperatures and the enthalpies and flows, those are shown in the diagram. The efficiency of LP heater number 3, if you calculate, comes out to be around 99.8%. Then you have got the fourth LP heater, that is low pressure heater number 4. The steam from IPT extraction E4 is given to the LP heater 4, and the condensate from LP heater 3 having a temperature of 125.27 degrees centigrade passes through the LP heater 4, and it gains a temperature up to 156.52 degrees centigrade. The flow is the same, and the LP heater number 4 also gets the leak of steam from HP and IP. The leak of steam from HP and IP, that is G3. So that steam, the leak of steam, is also added into the LP heater 4, which heats the condensate. The drain of this heater, it goes to LP heater number 3, that is through the HD4. If you calculate the efficiency of the LP heater 4, it comes out to be around 99.7%. Then we have got the feed tank. The condensate from LP heater number 4, it goes to the deaerator feed tank. So it goes to the deaerator and the feed tank. The deaerator receives the steam of the gland leakage from ESVs and IVs. Some gland leakage is there. That steam goes into the deaerator. Similarly, steam supply to glands, that is given from the deaerator. From the deaerator supplies the steam to glands. Again, the deaerator supplies the steam to ejectors also, main ejector and GC1, that is D2 and D4. Then it receives the pegging steam. The pegging steam is also from PRDS or extraction 6. This steam is added into the feed tank as a pegging steam. Then drains from LP heater 5 or 6, LP heater 5 or LP heater 6, whichever it may be, HD5 or HD6. It also goes into the deaerator. The total from the deaerator feed tank, the condensate, the temperature of the feed comes to 166.71 degrees centigrade if you measure, and the BFP boiler feed pump sucks the feed water from the feed tank. The suction flow, we measure the suction flow. The suction flow was around 652 tons or 652,000 kg. So the feed water goes to the, from here, after the BFP, the feed water goes to the HP heater 5. Now here the temperature of around 6 degrees centigrade is more than the inlet temperature to BFP. The deaerator efficiency you can calculate, and the deaerator efficiency comes to 96.8%. The deaerator steam supply, there are some deaerator steam supply changes. So the deaerator is supplied with heating steam from extraction tapped from either extraction number 5 or extraction number 6. Extraction number 5 is taken from IPT and extraction number 6 is from HPT at HPT exhaust. Now how the changeover is there? For loads below 150 megawatt, deaerator heating steam is derived from extraction number 6, which is changed over to extraction number 5 at loads above 150. When the loads go above 150 megawatt, then the changeover is there. Auxiliary steam supply to the main ejector, gland steam ejector and sealing steam of turbine glands is changed over from auxiliary PRDS to deaerator. The deaerator pegging steam supply is initially given from auxiliary source to extraction number 6 at about 90 to 100 megawatt of load. So this is about the steam supply to the deaerator. Then the drains, drains cascading. The gland leakage steam from the ESV and IV is also fed to the deaerator. Heater number 5 and 6 drains are also fed to the deaerator. Actually, HP heaters are taken in service after 60 to 70 megawatt load is taken on turbine. Heater number 5 drain goes to heater number 4 for loads less than 150 megawatt. For turbine loads more than 170 megawatt, heater number 6 drain goes to heater number 5, and heater number 5 drain is diverted to deaerator instead of heater number 4. So when you are running on 210 megawatt, definitely the heater number 5 drain is going to heater number 4 and then to deaerator. Heater number 5 drain goes directly to deaerator and instead of heater number 4. Now the boiler feed pump. The total quantity of feed water supplied from feed water tank to boiler feed water pump is equal to the must be equal to the main steam flow over to the HP turbine. The heat added by the boiler feed pumps due to mechanical churning of water, because it's a high pressure pump, is also taken into consideration, and it equals to, you can see that the feed water suction has got a temperature of 166.71 degrees centigrade, but the outlet temperature comes out to be 173.12 degrees centigrade. With the flow of 652 tons or 652,000 kg, you can see the heat gained by the feed water is of the order of around 41,79,320 kilocalories. Then next in the regenerative cycle comes the high pressure heater number 5. Now the high pressure heater number 5 receives the extraction steam from IPT, extraction number 5, E5. It also receives the drain from the HP heater 6, HD6. It receives feed water from the BFP discharge. Feed water flow is 652 tons, and the temperature of the feed water from BFP discharge is 173.12, and the gain in the HP heater 5, temperature gain of the feed water into heater number 5. So it gets the temperature rises to around 189.69 degrees centigrade. The drain of the deaerator is cascade. The drain of the is HD5 goes to the drain to this goes to the deaerator. This drain goes to the deaerator. The efficiency comes to 93.7%. Now the steam from the feed water from HP heater number 5 goes to HP heater number 6. The HP heater number 6 receives the steam from HPT extraction E6. It receives drain from the HP heater number 7, and it is also supplied with spindle leakage from HP turbine. That spindle leakage, as per the design, the pressure and the temperature and the flow has been taken as per the design. The enthalpy, as wrongly it is 586.350. The steam from the drain goes to the HP heater number 5. If you calculate the efficiency of HP heater number 6, it comes out to be around 99.7%. Then high pressure heater number 7, it gets the extraction steam from the HPT E7. The steam temperature and pressure parameters are there. The feed water from HP heater 6 enters into the HP heater 7 with a temperature of 228.80 degrees centigrade, and the temperature rises to 253.94 degrees centigrade. The drain of this heater goes to HP heater number 6. If you calculate the efficiency, that would come to around 99.5%. Well, the regenerative section is complete. Now the feed water, it enters into the boiler, and then from the boiler economizer, then it goes to the boiler drum, then from the superheater, and then it enters into the main steam into the HP turbine. So the main steam inlet pressure is 130 kg per square centimeter. Temperature is 535 degrees centigrade. The flow is 652,000 tons, 652,000 kg, and enthalpy is 819.94 kilocalories per kg. There are total 12 stages in the HP turbine. One extraction is there, E7, that is after the 6th stage. The various parameters are also shown in the diagram. The CRH pressure the exhaust pressure CRH pressure is 28.07 kg per square centimeter. The temperature is 327. Now the extraction E6 is also taken from the cold reheat. This we call as the cold reheat. So some of the steam goes to the extraction 6. The amount of steam that goes to the HP heater 6 is around 40,391 kg, and the flow to the going to the reheater is 566,369 kg with enthalpy of 732.99 kilocalories per kg. You can calculate the high pressure turbine heat given to the high pressure turbine. The heat given to the high pressure turbine comes out to be 119458,067 kilocalories. This much heat has been given to the high pressure turbine. Now the outlet of the the outlet from the HP turbine goes into the boiler again into the reheater, and then it is supplied to the IP turbine. So hot reheat, that is IP turbine, the pressure is 24.69 kg per square centimeter. The temperature is here again the raised in the reheater, that is 535 degrees centigrade. The flow would be the same. Then the enthalpy is 845.83 kilocalories per kg. The various extractions are there, E3, E4 and E5. These extractions are there, and the various parameters of the extraction, pressures and temperatures are shown here. There are total 11 stages in the turbine. E5 is after this third stage, E4 after the sixth stage, and E3 after the ninth stage, and E2 at the 11th stage. So these are the 4 extractions. So the various extractions are shown here, and the exhaust is of this is going into the LP turbine. The heat given to the IP turbine can be calculated. The flow and enthalpy are known. So it comes out to be 159617794 kilocalories. This much heat has been given to the intermediate pressure turbine. Then from the intermediate pressure turbine, the steam enters into the IP turbine with the parameters shown here. Pressure is 1.369 kg per square centimeter. The temperature is 183 degrees centigrade. The flow is 470,857 kg, and enthalpy is 678.41 kilocalories per kg. There is one extraction here. So there are total 8 stages, 4 stages to left hand side, 4 stages to right hand side, and the extraction one is after the third stage of both the sides. So the extraction parameters are also given, and the steam exhaust from the LPT is of the pressure of around 0.0889 kg per square centimeter absolute. The flow is there are 2 outlets, so going into the 2 twin condensers, it is 23,004 kg per square kg, and temperature is 43 degrees centigrade, and enthalpy is 589.18 kilocalories per kg. The LP turbine, so the total heat given to the LP turbine comes out to be around 48406583 kilocalories. In a short, you can see the heat given to the high pressure turbine, heat given to the IP turbine, and heat given to the low pressure turbine, and the total heat input given to the turbine cylinders. The addition of all these 3, it comes out to be around 327,482,444 kilocalories for generation of 211,902 kilowatt hours of power. The extraction quantity and the heat tapped. Now there are some extractions which are taken out from the turbine. Those are E1, E2, E3, E4, deaerator, E5, E6 and E7. So all these extractions, various pressures, the temperatures and the flow, those are there. The total heat is also calculated here, and you can see from there you can calculate the quantity of extraction flow. The total quantity of flow per hour means total quantity of extraction flow is 177,088 kg per hour, that is around 177.088 tons per hour. Percentage of extraction flow, this is the of the order of around 27.16%, and the percentage of heat tapped, if you calculate, it comes out to be around 39.61% of the heat has been tapped. The heat regained by the feed water and efficiency of the regenerative feed heating system you can calculate. So up to LP heater number 2, the heat regain or the heat gain is 277.02116 kilocalories. After LP heater 3, that much is the heat gain. After deheater, the heat gain is given there, 565.8313 kilocalories. In the BFP also you gain some heat. After HP heater 7 also you gain some heat. So the total heat gained by the feed water is calculated as equal to 121141,330 kilocalories. So the heat lost in the feed water regenerative heating cycle can be calculated. That would be equal to the heat in the extractions minus the heat gained by the feed water. So heat lost has been calculated and it comes out to be 8605482 kilocalories. This was the heat lost in feed water regenerating cycle. So the efficiency of the regenerative feed heating system can be calculated and it comes out to be around 93.36%. This is the efficiency of the regenerative feed heating system. Now the steam, after the LP heaters, the steam is going into the condenser. So the condenser, you have got the condenser, the cooling water from the cooling towers or from the CW pumps, it enters into the condenser with a temperature of around 30 degrees centigrade and the flow of around 27,000 meter cube. It receives the steam from the LPT. The flow is 230,004 kg with the enthalpy of 589.18. The condenser also receives the drains from GC1, GC2, LP heater 1 and ejector drain. All these drains are shown there in the green line and the total flow, the flow is also shown. So the total drains and this flow, that is, and the makeup has been stopped completely here when we are calculating a heat balance. We have stopped the makeup and the total flow through the CEP, it comes through the CEP is around 480,106 kg. This much is the flow. The pressure is 22. The discharge pressure of the CEP is 22 kg per square centimeter. The temperature is 43 degrees centigrade. Now if you consider the outlet temperature of the cooling water to around 41.6 degrees centigrade, that means around 11.6 degrees centigrade, and the condenser efficiency of around 80%, then the requirement of cooling water would be around 58.69 kg of cooling water for per kg of steam. This would be around required. Some more condensers details. Two condensers are connected in parallel. Heat lost in the condensers is equal to the enthalpy of steam at LPT exhaust minus the enthalpy of hot well water into the quantity of steam at LPT. So that comes out to be 251173568 kilocalories, or you can for 210 megawatt, or if you calculate the kilowatt hours, it comes out to be around 1185.32 kilocalories per kilowatt hour. The total condensate from the hot well is extracted by the condensate extraction pump and passes through the regenerative feed cycle before entering the economizer in the boiler. The cooling water requirement that has been calculated as this, considering the rise in the CW temperature from 30 to 41.62 degrees centigrade, that is 11.62 degrees centigrade, and the efficiency of the condenser to be around 80%, then the requirement of cooling water will be equal to the turbine exhaust heat lost due to the cooling water divided by condenser efficiency and divided by rise in CW temperature. So it comes out to be around approximately 27,000 meter cube per hour. The cooling water requirement would be around 27,000 meter cube per hour. The quantity of circulating water would be for the steam would be around 58.69 kg circulating water per kg of steam. This much water would be required. For calculating the turbine cycle heat rate, the heat rate would be equal to the total heat supplied to the turbine in kilocalories divided by the total generation in kWh. So the total heat supplied to the turbine can be calculated by the Q1, that is the live steam flow, multiplied by the enthalpy of the live steam is 819.94. IW is the enthalpy of feed water. QR is the reheat steam flow. I3 is the enthalpy of the reheat steam. I4 is the enthalpy of the cold reheat steam. And W is the total power developed in 1 hour, that is in kWh. So if you calculate with the formula given, or with this you calculate, the turbine cycle heat rate comes out to be 2043.11 kilocalories per kilowatt hour. So you can say that at 210 megawatt the heat rate would be 2043.11 kilocalories per kWh. This heat rate can be calculated at various loads, keeping the load constant at a particular 180 megawatt, then at 160 megawatt, at 150 megawatt, like that, and then the heat rate can be calculated on all these loads. So thanks for watching. Like, share and subscribe our channel, Total Output channel, and goodbye. I am Manohar Tatwadi. Goodbye to you till the next video. Thank you very much.